Good day. So now I'm going to introduce to you one of the most familiar concepts in physics, which is of course voltage. Okay, so we're familiar with it, right? We always see it on labels and markings of electrical equipments. But what really is voltage? And on a side note, to understand, of course, the concepts that falls under it. So primarily, electric potential energy, which is actually just potential energy but in the realm of electricity. Then we have electric potential, so this is what voltage is. Then potential gradient, and then lastly equipotential lines. Alright, so this will be the objectives that you should keep in mind while we're discussing the topic. Okay, so I will be showing you an illustration which I have prepared earlier here, and then show you the explanation of the topics that we're going to cover for this lecture. Okay, so what really is a voltage? So voltage is also known as, okay, so let's reduce this. Voltage having a symbol V, which is also known as electric potential. Alright, so this is capability of a charge to travel the electric field. Okay, so this is the definition of the potential in its name. Alright, kumbaga kakayanan, no? The potential, the capability, alright, of a charge to travel the electric. I will be explaining it through the illustration that you can see above. Okay, on that note, so we have electric potential energy, or EPE. Alright, so this is also known as EPE. Symbol natin for this one can either be just potential energy, or you can place a marking that this is about electricity. So PE sub E. Alright, so this is the energy. Alright, so take note, this is this is energy. Alright, so needed to get the charge across. Across the electric field. Okay, so by the way, going back, so for voltage, the unit for this is volts. Right, it's SI unit. So this is small v. Okay, then we have electric potential energy. Of course, this is energy, so the unit is joules. Okay, then let's have potential gradient. So potential gradient is basically the relationship between the electric field and distance. Alright, so this is what I will be showing later in the illustration. Distance between the plates. Okay, so if you're having a uniform electric field, which of course can only be completed if you have two plates that are facing each other. So the strength of the electric field in that particular coverage or distance would have of course an effect on the electric potential. So that is what potential gradient is. Then equipotential lines. Lastly, so these are lines that defines the potential gradient. Alright, basically the concept of potential gradient and equipotential line is under voltage. Then there is a relationship between energy and voltage, which I will be showing through a series of what do you call this? Derivation, which I will be showing on this side, I guess. So you can read this naman, right? So first, let's take the concept of work. Okay, then you take a look at the illustration that I have here on the left side. So work, according to work energy theorem, work is equal to kinetic energy, correct? So that means kinetic energy is of course the opposite of potential energy, right? So work is equal to negative potential energy, right? So just remember that the purpose of this derivation is for you to understand the illustration that we have here. Okay, so let's take a look at this first diagram, wherein we have a proton or a positive charge that is placed on a positive plate. Alright, so its potential energy is at its maximum, right? While the kinetic energy is 0. But of course, it will gain a kinetic energy because, as we know, positive plate, so this is a positive plate, right, will of course repel the positive charge. So what will happen? It will move towards the negative plate. So what would happen is its maximum potential energy will be decreasing over time. Then its work will increase over time, which is of course increasing the kinetic energy as well. So that's the purpose of this derivation, to show you the relationship between work, kinetic energy, and potential energy between between the electric field and of course the charge that is placed in it. Okay, so that's the purpose of that. So you take note of those, okay? Kasi at the final answer, you will be putting everything in absolute value, as you may have understood from the previous discussions that we have now. We don't have negative magnitude for concepts in electricity. Okay, that designates mostly if the attraction is an attractive kind or a repulsive kind, the rule of action. Okay, anyway, going back, so of course we also know that energy can be defined in terms of force, right? So we can take work as force times distance, correct? So that would mean electric field, potential energy is equal to force times distance, right? And then of course we had the definition of force from the electric force, right? The Coulomb's law. So that's F sub E is equal to charge multiplied by the electric field. So this charge is the one that is placed on the field, right? So substituting this electric force on the previous equation that we have, so we now have potential energy is equal to QED. Okay, so this is the first relationship that I want you to remember. But of course, if you're going to utilize this in, what do you call this, problem solving, you're going to place absolute value on everything. The meaning of this is, you take a look. All right, so if you place a charge on the side where it will have the maximum potential, you get that? It will have the maximum potential because there will be a possibility for the object to be moved, right? If you remember from the previous lesson from General Physics 1, right? The formula of potential energy, let's say you have, what do you call this? A rock on top of a hill of a boulder. Its potential energy is at its highest, right? Because if you translate its equation, that's mass times acceleration due to gravity times height. So the more you increase the height, the higher the potential energy becomes, right? Because this increases as the height increases, right? Because of course it's acceleration from let's say after 1 second the speed would be 9.8 meters per second, but after 2 seconds that would be twice as that. Okay, and the distance will be covered is, I think, quadruple as that. You can check it on solving. So that's the same case that applies here. So as you are placing it further and further from the side where it will be attracted to, the potential energy increases. Okay, so of course it decreases because from the equation that we have here, it decreases because it will be moving on what we call this. So this is what the potential gradient is. Okay, so as you move along the gradient, okay, so the potential energy gets lesser and lesser. All right, so the kinetic energy increases. So that's the takeaway from there. I hope you get the explanation why we place negative sign on the equation. But of course, upon using it, you will know that, I mean, you will see that you will only need positive values. All right, so you can also say the same thing here on the second diagram. So you have an electron placed on a negatively charged plate. Of course, it will be attracted to the positive plate, right? So it will move through that direction, right? So as indicated by the red arrow, the dashed arrows. All right, so of course its potential energy is at its highest on this place. Okay, then as you move further across the gradient, so potential energy gets weaker and weaker. So the purpose of these lines, so those are what we call the equipotential lines. It indicates the value of the electric potential or the voltage on the if, for example, the electron has moved instead of here, it will be placed here. So of course, the voltage will be different from this side. Why, sir? Because the formula for voltage can also be found on this equation. So that would be, you can rewrite it as negative potential. Or we can just rewrite it in a way that we're going to use it on the problem solving. So that would be QV, since remember this equality, voltage is equal to electric field times distance. So this equation is what constitutes the definition of potential gradient. So you can see the relationship of electric field, distance, and actually voltage for that matter. Okay, so this actually has a negative sign here because as you move closer and closer to what do you call this, the plate where it will be attracted, the potential gets weaker and weaker. Okay, let's say your voltage here on this side is, let's say, 20. I'll be illustrating it here. Okay, 20 volts. Then as you move across the gradient, the voltage you will be needing will be less. Okay, because of course it has covered already a certain distance. So let's say here it will be 10 volts. The reason behind is because you have covered this distance already. Okay, so the distance will of course decrease, but the electric field will remain constant. It doesn't change. Okay, so because this is a uniform electric field, so what would happen, of course, the voltage will increase, it will decrease as the distance increase. You get that? Okay, I will be showing it more on the following practice problems. All right, so, and then finally we have, we can rewrite this equation as voltage is equal to P over Q. Okay, so you have this one, which is basically the definition of electric potential energy by utilizing the concept of what do you call this, potential gradient. Then you have QE, which is electric force, right? And then finally E for electric field. Okay, then this will be the forms of derivation that you can use to arrive on the values that you will be needing. Okay, so we will be having some practice problems to elaborate further on this matter. All right, so let's have let's proceed on guided practice problem 1. Yeah, here. Okay, so the first problem would be, how much work does the electric field do? How about we just proceed on this one, and then let's just place it here so we can proceed on solving it. Yeah, okay, so here, so here's our first problem. So how much work does the electric field do in moving a negative 1.8 microcoulomb charge from ground to a point whose potential is 90 volts higher? So it says that we have, I'm just going to copy the rectangle here. Okay, so it won't be difficult to draw. So let's place this rectangle here. Then according to the problem, is placed on the ground, right? Then it will be moving to place where it is higher. Okay, so we have charge that has a value of 1.8 microcoulombs. Okay, so I'm going to draw an electric field. So if the charge is negative from the ground, that would mean this will be the electron and it will be moving up. Okay, so that would mean this state are positively charged. Then you have your charge here, which will be moving on this direction. Then of course you have an electric field, which is this one. Okay, so let's try to derive. Yeah, okay, so you can use the derivation, but I will start using the equality. Okay, so that would be, okay, so let's take a look again on the problem. It says it will be moving to a potential that is higher. Okay, so it means it's gonna go against its, what do you call this, its orientation, right? Because it will be moving from 0 voltage to a place where basically the translation and the equation will still be the same. Okay, something like that. Oh, how about let's try to write the necessary information first. So we have a charge which is an electron. So basically this will just be 1.8, or let's just place the charge, 1.8 microcoulombs, which is equal to negative 1.8 times 10 raised to negative 6 coulombs. And then we have voltage, which is of course 90 volts. Okay, so required of course is work. Okay, so for our equation, since negative potential energy is equal to work, okay, so you can just replace it with, then we have what, a negative PE equal to QV, right, which is can also be written as QV is equal to W. Okay, since you will be having both the negative sign, so that will be fine. Okay, so I hope you got the explanation on the illustration. So let's place the negative charge here. It will be placed here. Okay, so it will be moving from a place where its potential is 0. Its potential at this point is 0 volts, right? Because it's already attached to it. But it will be forced to move to a place where the electric potential is higher. Okay, so I hope you got that on the illustration. On the solution, it won't really show that much, so you can just plug in the values. Okay, so of course there's no such thing as negative work, so what you're going to do is have the absolute value, so that this will be at 1.8 times 10 is the negative 6 coulombs multiplied by, what's our voltage, 90 volts, equal to work. Okay, so there's that. You can show the derivation for, by the way, let me show you the derivation. I'll just show you the derivation of voltage, why we can obtain electric field, I mean the unit of actually I'm just gonna show you the unit of voltage when it is derived. Alright, so starting from potential energy, right? So this is joules, okay, which is equal to QED. Alright, then E as a unit of newtons per coulomb, right? Then D as a unit of meters, correct? Since you have C here, this is coulombs as well, so that's coulombs times newton per coulombs times meter, or you will be cancelling this out. So as you can see, the final answer for this will be Newton meter, which is of course equal to joules. So we're going back to the unit which is there, potential energy. So where would the voltage enter on this part? So taking ED, which is of course equal to V. Alright, so what's our unit for E again? So this is Newton meter per coulombs. Alright, so that would be the equivalent value of voltage. So if you want to derive the unit of voltage from the previous topic that we have, you will be arriving on this value. Okay, so that would mean electric field. So I'm going to show you, okay? So that would mean electric field is equal to B over D. Alright, I won't be showing you the explanation of the negative sign here already. I just want to show you the derivation. So in this case, this is what? Newtons per coulomb, right? Our unit for electric field. Then since we have voltage here, which has a unit of Newton meters per coulomb, multiplied by I mean multiplied by 1 over meter, right? Because this is division, so this will be how it looks like. So as you can see, you can cancel this out. See? So Newton per coulomb is also equal to volts per meter. Isn't that neat, right? So this is one of the most, I don't know, important relationship between electric field, and then for that matter, since you have Newton here, electric force, voltage, and distance. Going back, so this is the equation that you will be needing, or I mean the solution. So for the final answer, you just write it. Okay, so our unit for this one will be in joules. So I just showed the cancellation using, of course, the cancellation that I have showed. Alright, so let's proceed. Yeah, okay. So let's have number 2. So we have potential difference. So potential difference is basically electric potential. Okay, so it was just worded in that way because you're dealing with the gradient. So the difference between 2 points in a gradient is the potential difference. So it's basically electric potential. Okay, so you can choose to illustrate this or not, but I'm just going to show you the derivation of the equation. Alright, so for the given, we have an electron. So I'm going to place the charge of the electron. Okay, so that's Q sub E. Maybe we will be needing it later. So this is what? 1.6 times 10 raised to negative 19 coulombs. Alright, then we have the mass of the electron. So this will be 9.11 times 10 raised to negative 31 kilograms. Next, we have the velocity. Okay, so initial velocity, which is, so there won't be a final velocity since our final velocity here will be 0. Okay, so for this one, this will be 6.0 times 10 raised to 5 meters per second. Okay, for our required, we're tasked to look for voltage. Okay, so let's try to look for the equation that we will be needing. Okay, so I will be writing on this side to derive. So let's start with, I think, F is equal to MA. How about that? Right, so let's try to start there. So we have F is equal to MA, and then F equal to QE. Then we have P equal to, or how about in potential energy? Potential energy would be QED. Okay, so we will be needing voltage. So, or let's have P is equal to ED. V equal to E. Okay, so we can equate these two. Okay, so we have MA equal to QE. Then since A can be rewritten in the form of a kinematic equation, right? So what equation can we use that won't be needing time? So that would be the fourth kinematic equation, right? So let's write using that equation. Okay, so that would be M. Let's rewrite that. Let's write that equation first. So that would be V squared is equal to V sub 0 squared plus 2AD. Right? Then we can just cancel this one because we won't be needing it. So our initial velocity, let's have negative 2AB equal to V sub 0 squared. Okay, so this will be our velocity. Next, let's have, I think we can approach this even better. How about we use kinetic energy instead? Yeah, since negative BE equal to KE, let's just leave it like this. So KE equal to mv squared over 2. See, this is easier, right? And then we can equate it as, then we can equate negative BE equal to QED or QV. We can have QV, I think. Yeah, QV. There you go. So finally, we can now set this equation as QV is equal to mv squared over 2. So the magic behind this equation is you can just rewrite the initial velocity on this one. It won't really matter because taking the delta m delta v will be mv sub 0 minus mv, something like that. Okay, for the completion of this equation, if you're going to write it as the difference between the initial and final, what do you call this, the initial and final velocity, or I mean the initial and final kinetic energy. By the way, this is reversed, so this will be where you're going to place it. Anyway, just always remember that you shouldn't have any negative values on your answer. Okay, so let's proceed. Yeah, I'm just gonna erase this. We won't be needing this equation. So you can now proceed on substitution. So or S for this one, you can move Q on the other side, since what we're going to need is just the voltage there. So we can now solve. So we have voltage, or the potential difference, is equal to mass, of course, so that's the mass of the electron, so that's 9.11 times 10 raised to negative 31 kilograms. Okay, then we have velocity, so that's 6.0 times 10 raised to 5 meter per second v squared over 2 times q. So what's our q? So that's 1.6 times 10 raised to negative 19 coulomb. So as you have seen earlier, the unit Newton meter per coulomb is synonymous to voltage. Okay, so there's your answer. So you can just solve for that one. So you're going to have the value for the voltage. Alright. Okay, let's proceed on guided practice problem number 3. Yeah. So this topic, I mean this question is a bit easier compared to the first two that we had. Okay. So the electric field between two parallel plates connected to a 45 volt battery is 1900 volts per meter. How far apart are the plates? Okay, so you can choose to illustrate this. It's hard to draw a very thin rectangle, but there you go. Okay, so let's have this rectangle. Then we're going to have an electric field. There's a value of something something which is placed here. Okay, then we have a 45 volt battery that powers this thing. Okay, so you can just place, well, let's place the 45 volts on, if you're going to start on this side, so this place has the maximum potential, so let's place 45 volts there. Okay, So let's have given. So given for the voltage, we have 45 volts. For the electric field, so feels different now having 2 units for the electric field, but it's fine. Just shows you the beauty of physics and the interrelationship between the concepts. Then we have the distance between the plates. Okay, so for the equation of this one, so this is easy. So what's the equation? V is equal to ED, right? There. So since we're going to need the distance, just divide both sides by E. So you cancel this one. See then the solution. So our solution would be, let's write it on this side. We have distance is equal to, what's our voltage? 45 volts divided by 1900 volts per meter. There, then you just show the cancellation, and that's it. Proceed on writing the answer. So distance will be having a unit of meters.